Hello everyone, let's see this question. Cylindrical pipe, radius r, rolling towards a frog, sitting on horizontal ground. Center of pipe moving with velocity v. To save itself, frog jumps and touching the pipe only at top. Okay. Air time of the frog is capital T, horizontal range is capital R, acceleration due to gravity is g. Then which of the following conclusions can we make? So frog must have some vertical velocity, right? And that vertical velocity should be such that it touches only at top. So we know that the maximum height of the frog is how much? It is 2r, isn't it? And if maximum height is 2r, let's say initial velocity is vy, then, or maybe I should use uy, okay, uy and u1. So then we can say that v square is equal to u square plus 2as. Now the velocity at the topmost point would be 0. So we would get this equation. So from here what do we get? We get uy is equal to 2gr root over. Hence the time of flight, which is what? 2uy by ay. Ay is g. So that would be how much? It would be 4gr root over by g, right? So that gives us the time of flight as option A. Okay, so that's done. Now we have to discuss range. So what will happen when the motion is imagined from the frame of the pipe? Then you can see that in the frame of the pipe, what will happen? The frog will appear to move with a velocity u1 plus v, and the cylinder is at rest in its own frame. So due to that, you will have a parabolic path, okay, and that parabolic path will touch the pipe only at one point. Okay, that parabolic path should touch the pipe only at one point. And if that has to happen, then what is the you can have different parabolas here, right? You can have different parabolas, but there would be a thinnest parabola which touches the circle at one point, and any thinner than that, if you draw a parabola, it would intersect. Okay, it would intersect. So this thinnest parabola, when will we get? This thinnest parabola we would get when the radius of curvature of the parabola matches with the radius of curvature of the pipe over here. And this can be proven mathematically. Okay, if anyone requires that proof, you can just tell in the comments. I'll give the proof for that also. But right now I'm just continuing with this result, that the thinnest parabola which touches the pipe only at one point must have same radius of curvature as the pipe. And the radius of curvature of the pipe is how much? It is r. So what we can say? We can say that the radius of curvature in the frame of the pipe, we know formula for radius of curvature is v square by an. So that will be how much? u1 plus v whole square by g in this case. Here v is the velocity of the particle, and but the v here that I am using is the velocity of the pipe. So that's why in the frame of the pipe, this is the radius of curvature. So this must be greater than, or in the limiting case equal to, the radius of curvature of the pipe. So what do we get? We get that u1 plus v must be greater than, or in the limiting case equal to, root over gr, right? So that means what? That means u1 is greater than equal to root over gr minus v. And now that we have the speed, the horizontal speed of the frog in the ground frame, it is how much? u1. We can find out the range, right? Range will be how much? Range is velocity along x-axis into time of flight. In this case, velocity along x-axis is u1 into time of flight, which is 4r by g root over. So u1 is how much? u1 is root gr minus v into 4 into r by g root over, which matches with option B. So these two are the correct options over here. Okay.